Okay, let's continue. Hope the light's still good enough for the notes legible, but it's getting dark. Now we stopped at the definition, the introduction of acid and base by the Arrhenius definition, which is stated acids are the substances are able to provide proton or hydronium in the aqueous solution with water, right? And then the base was defined as the substances were able to provide hydroxide, OH 1 minus anion in the aqueous solution with water. And then that is the definition. Then we gave you a couple of those three examples of common acid, hydrochloric acid, nitric acid, and sulfuric acid. That's the three of the common they used in chemical lab, and that's a strong acid. Now some of the chemists may argue sulfuric acid is not considered as a strong acid to them, but not to me. All right, it is strong. The first hydrogen in there, the two hydrogen attached to sulfate, will be 100% dissociated in the aqueous solution. Nothing left. Become hydronium and hydrogen sulfate. But hydrogen sulfate can continue to dissociate almost complete, not 100%, but complete, and then under certain condition, like under reaction condition, 100%. But it's a self-dissociation or self-ionization is about 0.01 mole per mole of the hydrogen sulfate. It's not weak, it's quite big, because that's not a small number in chemistry. All right, the concentration is pretty high. All right, so this is the acid. Then we cited a few of just one of these weak base. Now we're going to introduce some strong bases, much easier to handle. This is a weak base, ammonia gas. Ammonia gas, people say, what is the acidity of this compound? Oh, it is acid, or it's a base, right? It is very basic. Why? Because if you bubble the ammonia gas, right, into the water, dissolving water readily, and then become a solution with a cation called ammonium, NH4, right? One proton attached to a neutral ammonia molecule become an anion, become a cation with a 1+ charged status, which is fitting to the cation carry polyatomic, right? Is that polyatomic? Yeah, oh, it is polyatomic, yes. But then you have a anion, OH, hydroxide, and 1 minus. That fits in the definition, ironic definition for base. All right, that is very easy to recognize. Then we may have a strong acid. That's a weak acid. This is considered as weak. Oh no, weak base. I'm sorry, weak base, because itself, the compound does not contain hydroxide inside, but it is able to dissociate other species, which in this case the solvent, water, to produce OH out of it. Now the rest of them are strong base, as we know the caustic soda. The caustic soda is sodium hydroxide, right? It's a solid pellet, and it's very easy to get the moisture absorbed and get wet. So we kept in the jar and stay away from moisture. And then if you drop this into the water solvent, and the dissolving water as a solvent, and then they give you a dissociation in water. So you have sodium 1+ aqueous cation in the solution, plus, right, plus the hydroxide, plus OH. Oh, this is better pen. 1 minus aqueous, because in the water solution, right? So that is what? That is 100%. Dissolving into the water as solvent, so dissolving there will dissociate 100% completely to this one. So this is a irreversible reaction. You call reaction dissociation, it's called reaction, because this species and these two are not the same species, right? So that's a strong base. Strong, very strong base. The strongest strong base. Right? Another one in the same family, alkali metal, so we can have a potassium hydroxide. It does the same thing, 100% in the water. Let's put the water underneath here. You still can see the potassium become 1 plus the cation in the solution. And with hydroxide, 1 minus aqueous. And this is also as strong as sodium. Right. So very strong. And then these are the base. Fitting to our next definition. When in the future we get into the acid-base chapter of acid-base, we'll have two more definition for acids, base, the classification. But we're not talking about here. One is loose, right? One is wrong, lower. All right, so Brown Statutory definition and Lewis definition. Not getting there. Yeah. Okay. So after we learned definition, we cited few examples. I think it's time for me to introduce my way of remember those formula. We are able to recognize those compounds would be acid or base. Right? In the acid base, we have 2 categories basically. Right? This is 2 categories. Right? Two categories. Of acids, and one is acids without oxygen. Another kind is called oxyl acid. Now here the O and A both has to be applied in this term. Oxyl means there's oxygen involved in the acids. Alright? So the acids without oxygen are those with halogens, right? And combined with the hydrogen. So with hydrogen, right? So the example for those were hydro, you use hydro, HYDRO, and with the halogen elements, right? Their name, the ending change into IC instead of chlorine and it's chloric, hydrochloric acids. That was what? That is HCl, right? And then you can have a hydro, right? Bromic acids with bromine, so you have HBr. Now those doesn't have oxygen involved. But if you have oxygen involved, right? Then you have oxygen depends on their number of oxygen involved. So that is one category for the acid, 2 category, 1 and 2. And the base always involve OH, but sometimes you don't see the OH like ammonia, and it is able to induce the water solvent into a OH provider, right? So that's the case. But for these acid and base, how do you recognize them easily? I find this is the way. All right, let's give you the generalized formula. Generalized formula for the, not the first type, the second type, oxyacid. Oxyacid with oxygen, right? Okay, let's put it this way. Let's say generalized formula for oxyl acids and bases. Right? Now, before we go there, we want to review the layout of elements in the periodic table of elements, right? Now, as we learned, this blue line almost fainted. And don't see much, but this blue line, right? The blue line right here, right? The blue line is zigzag stairway blue line, which separates the metal and non-metal, right? In the periodic table, right? But I already mentioned in the previous parts, I talked about those, whoever the box belong to, any elements as long as it touches the line, even the corner, like a carbon. The box of carbon, the corner touch the blue line, that is element we consider as a semi-metal or metalloids. Not considered as non-metal or metal, because those elements possess exactly what definition of a metalloid or semi-metal are defined with both the characteristics of metal and non-metal. Why should we kick them out of the category called metalloid? We have to keep them and consider them as metalloid or semi-metals, okay? But from this region on the left, they always are these metals. They always form positive charged cation by losing electron. 1, 2, 3, whichever the, maybe 7, up to 7, right? But they are considered as electropositive elements on this region, metal. And past the zigzag line for the semi-metal, we get into non-metal region, we consider them as electronegative elements, right? But they still can form compounds. The metal and non-metal, which is the electropositive, combined with the electronegative elements, their atoms can make ionic compounds, either binary or polyatomic, right? We already talked about this. But then, if you consider the non-metal area, right, even they are all non-metal, but we already talked about, right, nitric oxide, right? And those were able to what? Form covalent bonded compounds, right? But then we are going to talk about this in the introduction of electronegativity. Right, today, in this section, I hope so we'll reach there. But before that, we're going to talk about these two areas, right? They are one particular function in forming acid or forming bases, right? So in this generalized formulas, let's put formulas, for acid, oxyacid, and bases. Okay, now, number one, for acids. The generalized form for acids is what? Generalized form for acids is the hydrogen atom, right? Combined with what? Combined with something with oxygen attached, the polyatomic anion. The hydrogen atom, now how many hydrogen atoms? Let's put a subscript X next to the hydrogen representing the value 1, 2, 3, 4. And then connect, let's hook up with the compound with a stick as a bonding. Let's call it a single bond, but could it be other situation? Single bond acid is very common, right? And then what are we going to attach to in there to the hydrogen? Is going to be a element, would it be showing a property as non-metals. Non-metal atoms. And then, right, then what? With Y number of oxygens. Now that's a generalized format. Generalized formula for oxyacids. Now here is what? The X can be, right, can be 1, 2, 3, 4. Sometimes it could be up to 7, right? Chromium, right? Chromic acid, dichromic acid, right? So that's 7 all the way to 7. Right, 7. Oh no, the hydrogen may not that big, right? And the Y can be 1, 2, 3 to 7. Alright, that's a possibility. Alright, so let's give you an example. Hydrogen. What about picking about 2? H2. Well, H2. What about a non-metal? Let's skip the carbon. Carbon and carbonate. Yeah. Carbonic acid is a acid. Let's skip carbon, right? And then let's choose sulfur. So S, right? That's non-metal, right? Non-metal. And there was oxygen. You name it. You want to give you 3 or 4. If it's 3, right? That's what? Sulfurous, right? Sulfurous acid. Right? Because 3 oxygen, right? And then if you have H2SO4, sulfuric acid. You're already familiar with these 2 compounds, just last part, right? Then we can have a sulfur replaced by what? By the phosphorus, right? So we have this H3PO3, right? It's what? Right? Phosphorus acid. And then H3PO4. We say phosphoric acid, because this is higher oxidation state for P is plus what? Plus 5. This is plus 3, right? This is plus 3. Okay, this is plus 5, and you put down here, this is plus 3 for oxidation state for the phosphorus. Alright, clear? And in this case, the X is what? X equal 2, right? And Y equal what? Y equals 3. Now this one, X equal 2, Y equal 4. Now this one, X equals 3, Y equals 3. And this one, X equals 3, Y equals 4, right? Y equals 4. There's more, right? For instance, perchloric acid, HClO4, could be considered as the strongest acid ever. This is probably stronger than the hydrochloric acid and the sulfuric acid, nitric acid, because this acid is so strong, so dangerous, has to be kept in the brown colored glass bottle, sealed off, or avoid the direct sunshine or lights, otherwise it will explode in your lab and then shred everything into pieces. So in this case, X is 1, right? This is what perchloric acid. X equal 1, Y equal 4, right? Every one of them, let's just name a couple. No, we skip nitric acid. Okay, nitrous acid. 2, right? So nitrous acid, right? X equal 1, Y equal 2. That's possible as well. So those were the examples. So what, let's check, is that H on the left? They all have H. What's the X number of H, right? Atoms. On the right is the number of oxygen, what we call oxyl acid, right? And then in the middle, everyone were considered as non-metal. Is there any acceptance? No. Non-metal, right? Non-metal. So that is, now that is acid. Now number 2, bases. Bases, all right? I still have, how many minutes? Oh, 11 minutes. Bases. The generalized form of base is what? It's a metal. It gotta be different. Metals connected with what? Connected with, let's put a parenthesis, OH, hydroxide, in Z number of XYZ, right? And there was a Z value, could be 1, 2, 3, 4, right? 1, 2, 3, 4. That's the generalized form for the base. The base was OH, right? Now we're not talking about ammonia without OH in itself, right? When we talk about some acid, the base has OH already. So let's say we have example, right? Example right here. Now we already cited, right? A couple of them. Let's pick up this one, rubidium hydroxide, right? Now this one is the OH that you don't need parenthesis because there's only one OH attached to rubidium. So this one, right? It's the rubidium hydroxide. hydroxide, right? Now, what is the rubidium? Right here. Right here. First family, right? First family belong to what? Alkaline metal, right? Always +1 charge oxidation state, and then OH -1. So they're 1-to-1 ratio. Rb stands for rubidium, and then the OH stands for hydroxide. So in this case, Z equal what? 1, right? Z equal 1. Now we already mentioned the milk magnesia, right? But this time we choose another one. Let's say there's a beryllium down there, right? Or use the magnesium or calcium. So let's see calcium oxide. The calcium is 2+, right? +2 oxidation. So you need 2 hydroxide to match to reach the achieve the neutrality for this compound as it's not strong acid, it's weak acid. Getting a little weaker to the right hand. So that's what calcium hydroxide. Hydroxide. Now what's the Z number? The Z value is 2, right? Z equal 2. Z equal 2. Alright. Now we mentioned aluminum, right? Or we are able to use boron. Boron number 3. The third family, right? +3 only. +3 as its oxidation state for the most members of the third family, boron family, except going down, and then you see +1. So if we pick boric acid, right? Now that's not the real boric acid formula. I'll give you the notes. They have a. Let me see if I have this. Here the boric acid is HbOH4. All right. Let's say this is a little bit different case, right? All right. So let's use aluminum then instead of boric acid. You already see on page 4. You have the table, right? All right. So the aluminum. Now aluminum. Right, aluminum 3+, +3, and it requires -3. -3 come from where? From 3 hydroxide. So you have hydroxide, there's 3 outside because this +3, these give you -1. So 3 times -1 is -3, and the +3 they all match and become neutral compound aluminum, right? Alumic, I think called alumic acid. Hope it's not right. Hope it's not wrong. But here Z is what? 3. Right? Z is 3. So now you have an idea. The acid base fit into those generalized formula. The generalized formula give us an easy way to remember and identify the regular acid base, right? And here is this one has a base, right? It's right here. Generalized formula. Right, generalized formula. Now, just about forget, but I normally don't. When we talk about a semi-metal metalloid, right? I said any box, even a corner like a carbon, touch the stairwell line, that would supposed to be considered as semi-metal, but most of the chemistry book and the chemist teacher teaching carbon as non-metal, but it's not, right? We already discussed in detail about 3 natural forms of carbon, diamond, charcoal, and graphite, right? The graphite, you can see the luster of the shining reflection, and it's good electric conductor for the electricity, right? So that is metal part, and then the charcoal you cook barbecue with, it looks like a mushy, ugly looking, like a non-metal powdery. But aluminum the same. I said, the box of aluminum had 2 sides belong to this stairwell line, semi-metal. Why? Let's put a asterisk here. Just put a asterisk here. This compound, Al(OH3), right? It can be reorganized into a formula fitting to the acid category. Let's see it. What about this? Put a 3H in front. 3H in front. And aluminum as non-metal, here is as metal, because the definition for base is metal and OH. Z number of OH, right? And for acid is H, X number of H, and the Y number of oxygen. Put non-metal in the middle, that's going to be the formula, general formula for acid. Here, look, if we leave the aluminum in the middle as a non-metal, this time it's metal as a base, but if we leave it in the middle, right, and put 3 oxygen behind, watch it. What is that formula fitting to? Let me take this out. It's going to confuse you. Yeah, aluminum. Right? That can be, oh, should be here, should be, on top should be aluminum hydroxide. Let me talk about hydroxide, right? That's the base, right? Aluminum hydroxide. Now here we rearrange it. Now that's the base, aluminum hydroxide. That's hydroxide, always base, right? We talk about. But here's what? Here's aluminum acid. Is what? HL non-metal O3. That fit into acid, generalized acid form. that's what is called aluminum acid. If it's not correct, and then let me know. I'll check tonight. And in this case, the Z is not applied. Well, X, Y. What's X? X equals 3. What is Y? Y equals 3. That is fitting to the, no, it's fitting to the acidic format.